This is the Minkowski spacetime diagram. The perpendicular axes represent the frame of reference we are in. The skewed axes represent the frame of reference moving in front of us with velocity v. The x-axis represents the position axis, and all of the points on it happen at the same moment relative to us in this frame. Also, all the lines parallel to this axis, each of them represents points that are simultaneous to us. So the line parallel to the x-axis is called the line of simultaneity. The lines parallel to the t-axis each represents points that are at the same position relative to this frame, to our frame. Also, in the moving frame of reference, the lines parallel to the x-prime axis each represents points that are at the same moment relative to the moving observer in that frame. The lines parallel to the t-prime axis each represents points located at the same location relative to him. We are in the xt frame, and we as observers stay on the t-axis always, and it's called our world line, while the moving observer stays always at the t-prime axis, and it's his own world line. Let's consider the time dilation using this Minkowski diagram. When the moving observer sees on his watch that 5 minutes or 5 hours passed on him since the last meeting between us, we would disagree with him, and we say that this time passed. See how we made a parallel line to our x-axis. We draw one of our simultaneity lines to see at which time this point falls relative to us. And so his time relative to us goes slow. Now let's consider the length contraction. The moving observer measures a stick of length 3 meters. The stick stays always parallel to his x-prime axis, because both ends of it should stay at the same time relative to him. Relative to us now, both ends should be measured at the same moment, so the stick will be on our x-axis or parallel to it. This shows how the stick looks shorter in our frame of reference. Now let's talk about twin paradox. The same scenario. Two brothers, a twin, one of them goes in a long journey and the other one stays at home. It doesn't have to be Earth actually. He just doesn't leave the frame of reference he and his brother were originally in. Now when the traveler returns back, he would see his brother older due to time dilation. But what if we changed the frames and looked at the problem from the perspective of B, the traveler? Can the opposite happen? Can B be the older one since he sees A moves away from him at velocity minus v? Who will be older at the end, A or B? Well, the solution goes as follows. We should remember that we don't have only 2 frames of reference in this problem, but 3 actually. The frame A, the outbound frame of B, and the inbound frame of B also. A does not change his frame of reference at any time. In the frame of reference of A, the traveler says that he reached his destination at this time, which for him it corresponds to this moment in A's frame. But A says you reached at this time. We can draw the simultaneity line of A also. In the return journey, the same happens, but notice something very important. Due to the instantaneous change of the frame of reference of B as it returns back home, a big jump in time happens in the frame of reference of A. For A, this changing of frames costs B some extra time on Earth. If we now switch to the frame of reference of B, the traveler, we see that here also the jump he made from the outbound into the inbound costs him also time in S frame. If we switch to the frame of reference of B inbound, we see that here also this jump causes him also extra time in A's frame. In other words, while the change of frames that B does takes place in no time for him, in A's frame it requires some time to complete, and hence, in all frames of reference, A lives a while longer than B. I hope you find it useful. Please either subscribe and follow the channel or give a like or a comment. Any of that would be very appreciated. Thank you.